The most important advantage, of course, is energy savings. And here the whole system was able to prove that we can save 10% over the whole operation.
We can reduce the switching losses in our module, but then also we can increase the switching frequency in the application, and then we lift the energy efficiency of, for instance, the entire train engine. So starting from transformator via the power converter to the engine. And this is then a big benefit for our customer.
This is the podcast for engineers, the podcast you just have to listen to if you're interested in what's going on in the semiconductor market. Today, we're talking about the Deutsche Zukunftspreis, the German Federal President's Award for Technology and Innovation. Our team, which was led by Konrad Schraml and Caspar Leendertz, joined forces with TU Chemnitz to develop the world's first 3.3 kilovolt silicon carbide MOSFET with a vertical channel and innovative copper contacting. Today, we're talking all about it. And I'm here with Konrad and Caspar. Why don't you guys introduce yourselves?
Yeah, thanks, Kelsey, for having us here. My name is Konrad Schraml. I joined Infineon in 2015 after I did my PhD in semiconductor physics. I was long time a project manager here at Infineon, developing new chip technologies. And since 2022, I'm now manager of the so-called low voltage chip development group here in Munich, and low voltage means in our case 650 to 1200 volts.
Not quite so low. Okay, awesome. Caspar, what about you?
Yeah, thanks for having us here. My name is Caspar Leendertz. I have been working for Infineon for 10 years now in the device design group of GIP Infineon in Munich. Yeah, I really love my job. We can use simulations to push innovations, to develop next-gen technologies, or also to help product development in a later phase. And that's exactly also what I did in the 3.3 kV project.
Great. Thank you guys so much for being here. And you mentioned it, the 3.3 kV. But before we get into the actual product we were nominated for, Konrad, maybe you can tell me a little bit about the Deutsche Zukunftspreis.
Yeah, as you said, the award is from the German president. It has basically two main criteria. It is a prize for a product which is highly innovative. So you have to show something which is far beyond state of the art. And the second pillar is that your product must be or must have a big benefit for the society. And it also has to create jobs in Germany.
Okay, and I guess we fulfilled all those three criteria to be one of the three finalists nominated. We won't find out until November if we've won yet, but we want to take the opportunity to talk a little bit about this innovation. Caspar, you mentioned the product itself. Can you tell us a little bit about what's unique about it?
Yeah, there are basically three aspects that sets our technology apart. Firstly, we have transitioned from silicon to silicon carbide, and that's a huge benefit. So, for example, to block the same electrical voltage with silicon carbide, we only need 1/10 of the thickness, and we can leverage this advantage to also reduce the chip size then. And this goes hand in hand with strongly reduced losses, 90% switching losses, for example. That's one part of the story. Mm-hmm. And secondly, we also worked on our chip design. We were able to design the MOSFET as a trench MOSFET with integrated body diode also for this high voltage class. And that's another big advantage in terms of shrinking the size and getting more chips on one wafer, so reducing costs basically. And the third major point is that we use copper for the contacting. So silicon carbide and these very high power densities that we reach are very challenging in terms of reliability. But if we combine the copper with the silicon carbide, we can also make a big jump in reliability and actually be 10 times better than standard technology.
Okay, so a lot of different things, using silicon carbide in modules, using the copper contacting, the trench design. It sounds like a lot of effort, a lot of things to think about. Can you tell me about the team that was involved, Konrad?
Yeah, it was a really big team, starting from people like Caspar doing simulations, doing all the layouting, over front-end technology. So we had to develop a lot of new processes in the chip environment. There are a lot of experts were involved from UPD, from development. And then, of course, also in the back end, we went into a new module. So that's the XHP2, which I'm having here in my hand. And also there we have a lot of new processes. We introduced the copper bonding, chip sintering, and designed the first high-power silicon carbide module. So you can imagine that it was a really big team, at least 50 persons in the core team and many, many more contributing to this. And after 6 to 7 years of development, we finally managed to bring the product now to the market.
Okay, great. So it sounds like we've definitely met the first criteria of the Deutsche Zukunftspreis, innovation. But the second one was benefit to society, right? So how does this new innovation really benefit society?
Yeah, our product, it contributes strongly to the energy transition. In order to master this challenge, we need basically 3 things. First of all, we have to change to 100% renewables in the electricity generation. We need the electrification of things which are so far powered by fossil fuels. And of course, we should use every kilowatt which we generate most efficiently. And here we come a big step forward in all 3 categories. And that's how we contribute to a better society and also generate a lot of jobs in Germany, because we have many companies here in Germany who use this kind of modules.
Mm-hmm. A lot of innovations are created to meet a demand. What was happening in the application space that caused us to think we needed to create something new here? What was going on in applications?
Yeah, when we started in 2017, silicon was still the standard. And if you switch such high voltage chips, they generate usually a lot of switching losses. And this limits the switching frequency which you can allow in the application. To be precise, the limit was around 1 kilohertz. Then such modules were at the thermal limit. But this 1 kilohertz, it's not enough. You want to switch more often and steer the current more precisely into the various system of your electronics. So for instance, in a train, you generate a lot of energy yield loss in the transformator or in the engine. And this was the point where we said, hey, if we go to silicon carbide, we can reduce the switching losses in our module, but then also we can increase the switching frequency in the application. And then we lift the energy efficiency of, for instance, the entire train engine. So starting from transformator via the power converter to the engine. And this is then a big benefit for our customer.
So Konrad, you mentioned trains and energy efficiency being an important aspect that we addressed with silicon carbide. Does silicon carbide also address anything else in trains?
Yeah, with the increased switching frequency, we can also reduce the size of passive components like magnetics, or we can get rid of filters. And this is a huge benefit for the electric drivetrain. So the whole system decreases in size and weight. This is a big thing for our customers because space is limited in trains, and it also helps to reduce costs.
Okay, let's talk more about trains, Caspar. What impact does it really have on the mobility, the rail transportation sector?
Yeah, exactly. Now that we have this module that is suitable for this very high power ratings, we can save the energy where it flows the most. For example, in rail transportation. And there's already an example where we were successful. And this example is a streetcar in Munich. This was running for 1 year and covering 65,000 kilometers here in Munich, and worked perfectly as a whole system. There, maybe let me mention two benefits. One is related to the audible noise. So the passengers and also the residents were very, very happy because this train is very quiet.
Okay, so this is the squeaking noise that it makes when it starts.
Exactly.
Right?
That's a kind of squeaking noise. And now with our new chips, we have so little power losses that we can switch so fast at frequencies that are difficult for the human ear to hear.
Okay, very nice.
That's one advantage. And then the most important advantage, of course, is energy savings. And here the whole system was able to prove that we can save 10% over the whole operation. And that's a considerable amount. You can imagine that it means per module 3 megawatt hours energy savings per year, and that's the amount of energy that a small family house would use.
Okay, and how many modules are in a tram, for example?
Yeah, this depends. A tram has around about 10 to 15, I think, but if you look at freight locomotive, then it's already 100. So you could save the energy of 100 family homes per year with one locomotive. And then, of course, you can imagine if you look at the whole German electric locomotive fleet, or even at other applications that you might be able to electrify and equip with our energy-saving module, there's a lot of CO2 savings we can achieve.
Okay, yeah, I like that ripple effect, that it may seem small, like a little bit of energy savings in one module, but that carries on so many modules per tram, so many trams for Germany and the world. It could really make a big impact. What else? You mentioned other applications could also be interesting. Konrad, could you mention anything else?
One highlight of the usage of this module is the generation of renewables, so in particular wind parks and solar parks. So basically everywhere where a lot of power is generated, you also must somehow steer this power to the grid. And maybe if you look at the windmills, in windmills also space is very limited. And power density is increasing and increasing with every generation. So here we have a very good match with this increased power density of the module. And another aspect here is the reliability issue. If you imagine that this thing stands somewhere outside in the sea and something breaks, then maintenance is very expensive. So having a product which has a very high power density and a very high reliability is really a key benefit for our customers there. Okay. And it helps to reduce then at the end the cost for current generations.
Okay, yes, I could imagine that sending a helicopter to an offshore wind park for a broken module would be a bit of a nuisance. So good that our reliability stands up there. So you mentioned generation, efficiency, and electrification, right, at the beginning of the episode. So what about electrification? Can you tell me more, Konrad?
Yeah, one prominent example is again in the train market. So nowadays, not all of our tracks are electrified. So we have diesel trains running a lot in Germany, but also in other countries. And here you can either electrify all the tracks, which is very costly. The better way would be to use trains which are operated either by hydrogen power or by battery electric systems. And if we maybe look at these battery systems, they consume space. Batteries, it may be from the cars, they need some space, and space is very limited in the trains. So if we can reduce the size of the power electronics that helps to get more range for these trains or reduce the weight. And here again, as I touched it before, this decreasing size and volume is a big story for our customers, and it helps to electrify these large drives, not only in the trains, but also in other things like ships or aircrafts, maybe.
So it sounds like there's a lot of opportunity for improvement with our innovations. So thank you, Konrad. Thank you, Caspar, for being here. And as I mentioned, we are going to dive a little bit deeper into the technical challenges and aspects of this innovation in the next episode. Until then, stay tuned and see you soon.